So the combined gas law, we have three variables we can work with simultaneously: pressure, volume, and temperature. A sample of gas occupies 125 milliliters at STP. That's giving you two pieces of information. It's letting you know it's at 0 degrees Celsius and 1 atmosphere. So what will the volume of the gas be at 65 degrees Celsius and 320 torr? We're solving for V2. So to solve for it, we first cross multiply. Whenever you have something in the denominator down here, you have to cross multiply to get rid of it. So we cross multiply. And we get P1, V1, T2 equals P2, V2, T1. And now we want to know the final volume, so divide each side by P2, T1. And whenever you do to one side of the equation, you have to do to the other side. And that is how they get their formula. And then we make sure the volumes or the temperatures are Kelvin. So STP is 0 Celsius, that's 273 Kelvin. And the final temperature is 65 Celsius plus 273 gives us 338 Kelvin. And we add it all in and we get 0.368 liters or 368 milliliters. And you're getting liters because they chose to use liters, because it was 125 milliliters and they put that in as 0.125 liters. Both would be correct. If you used milliliters, you just get 368 milliliters, and that would also be correct. Until we get to the ideal gas law, the units that you use for volume or pressure aren't that important yet, as long as you're consistent throughout. But temperature must always be in Kelvin. What is the volume at STP for a gas that occupies 1.62 liters at 616 torr and 42 degrees Celsius? Again, STP gives you two pieces of information: 0 Celsius or 273 Kelvin and 1 atmosphere pressure. So you are again solving for final volume. So just like back here, we cross multiplied and then divided each side by P2 T1 to isolate, because again, P2 divided by P2 is 1, T1 divided by T1 is 1, leaving us volume. And then we plug and chug. It's important to remember that temperature must be in Kelvin. Everything will be wrong if temperature is not in Kelvin. It is essential to use Kelvin temperature for all gas law problems. And we get our answer of 1.14 liters. A balloon is filled with 266 liters of helium gas, measured at 38 Celsius and 0.995 atmospheres. What will its volume be when the temperature is lowered to negative 76 degrees Celsius and the pressure is 0.561 atmospheres? Again, same exact scenario. You're finding volume 2 like we did last two times. We cross multiply like we did. And you get P1 V1 T2 equals P2 V2 T1, and you divide each side by P2 T1 to isolate V2 to get our equation. And that's the hardest part of the problem. Then we just plug and chug. We remember that we have to convert Celsius temperature into Kelvin, and we get 299 liters. And that's the kind of math that you would use for like a weather balloon that's going to be really high in the atmosphere. It can be extremely cold. The ideal gas law. This is a single equation relating all properties of a gas. This is bringing in a new variable, moles. N is the number of moles of a gas. So the pressure times the volume equals the moles of the gas times R, which is the universal gas constant, times the Kelvin temperature. Now the universal gas constant has some interesting units. R in this class will always be 0.0821 liter atmospheres per mole Kelvin. And because the units of R have liters, atmospheres, moles, and Kelvin, all the other units have to cancel those out. So as always, temperature must be Kelvin to cancel out Kelvin, but it's always been Kelvin, so there's no change yet. And moles is always moles. But when you use the ideal gas law, pressure must be in atmospheres. So if you're given pressure in torr or millimeters mercury, you must convert to atmospheres so that it will cancel out with those atmospheres. And volume must be in liters to cancel out with those liters there. And in every problem, R is always the same because it's a gas constant. R is always equal to 0.0821 liter atmospheres per mole Kelvin. So how many moles of helium are contained in a 0.9 liter container of 30 degrees Celsius and 0.8 atmospheres? Well, we're solving for moles. They want to know how many moles of helium are there. So we divide each side by RT. Whatever you do to one side, you do to the other. And RT divided by RT is 1, just leaving N. So N equals PV divided by RT. And that's the hard part right there, is doing the algebra to set your equation up. Now we make sure pressure is in atmospheres, because it's the ideal gas law. And it's already in atmospheres, so you're good. We make sure volume's in liters, because it has to be liters to use the ideal gas law, but it already is, so you're good. And then we convert temperature into Kelvin. 30 plus 273 gives us 303 Kelvin. And R is always 0.0821 liter atmospheres per mole Kelvin. And so we multiply and divide, and we get 0.0289 moles. And again, this atmospheres cancels out with this atmospheres. Kelvin divided by Kelvin is 1. Liters divided by liters is 1, leaving you the units of 1 divided by 1 divided by mole. And when you divide by a fraction, you flip it and multiply it. So instead of saying 1 divided by 1 divided by mole, we can say 1 times mole divided by 1, which gives us moles. So whenever you divide by a fraction, you flip and multiply. What volume will be occupied by 0.393 moles of nitrogen gas at 0.971 atmospheres and 24 degrees Celsius? Well, PV equals nRT. Pressures in atmospheres already. We're solving for volume. We're going to have to convert temperature to Kelvin. But to solve for V, we divide each side by P. P divided by P cancels out. So volume is nRT divided by P. And we plug in 0.393 moles for N, 0.0821 liter atmospheres per mole Kelvin, because that's what R always is. 24 Celsius plus 273 gives us 297 Kelvin divided by 0.971 atmospheres for an answer of 9.87 liters. The ideal gas law can also be written in terms of molar mass of a gas. So grams divided by moles is the same thing as moles. Because as we just said, when you divide by a fraction, you can just flip it and multiply it. And so instead of dividing by grams divided by moles, we can flip it. And so we can say grams times moles divided by grams gives us moles. And so this lets us put in the mass of the grams, the mass of the gas in grams, divided by the molar mass of the gas to give us moles. So we can change PV equals nRT into PV equals the mass of the gas times RT divided by the molar mass of the gas, which is grams per mole. So a 0.210 gram sample of gas has a pressure of 432 torr in a 333 milliliter container at 23 degrees Celsius. What is the molar mass of the gas? Well, We're using the alternate form of the ideal gas law. We're replacing moles with mass divided by molar mass, because grams divided by moles is the same thing as grams times moles divided by grams, which is moles. And we're solving for m. So we cross multiply. There is nothing under PV, so you just put a 1 there, because PV is the same thing as PV divided by 1. And we get PV capital M for molar mass equals GRT. Now to isolate molar mass, we divide each side of the equation by PV. And P divided by P is 1, V divided by V is 1, giving us our equation. And then we plug in 0.210 grams for the mass of the gas. R is always 0.0821 liter atmospheres per mole Kelvin times the Kelvin temperature. 23 Celsius plus 273 gives us 296 Kelvin. And then in the bottom we have the 0.568 atmospheres, which they converted from torr. So 432 torr times 1 atmosphere divided by 760 torr gives us 0.568 atmospheres. And then we converted 333 milliliters into 0.333 liters. And the liters is down here. It should be over there. Make more sense. And we get an answer of 27 grams per mole. Calculate the molar mass of an unknown gas of 0.768 grams occupies a volume of 754 milliliters at 30 degrees Celsius and 342 torr. Well, we convert milliliters to liters, 0.754 liters. We convert degrees Celsius to Kelvin, add 273 to get 303 Kelvin. And we convert torr to atmospheres. 342 torr times 1 atmosphere divided by 760 torr gives us 0.450 atmospheres. And then we plug and chug. The mass of the gas, which is given to you, times R, which is always 0.0821 liter atmospheres per mole Kelvin, and again the mass of the gas was 0.768 grams, times the Kelvin temperature, 303 Kelvin, divided by, and when you do this in your calculator, you should put the entire denominator in parentheses so your calculator knows all of it is in the denominator. 0.450 atmospheres times 0.754 liters gives us a molar mass of 56.3 grams per mole. And for some reason the answer up here rounded it.